The goal of this video is to show how to control an underactuated system. In an underactuated system, the number of degrees of freedom is more than the actuators, and so it is usually kind of difficult to control such systems. We're going to specifically look at a double pendulum. Here, there are two links, but there's only one actuator. If there's one actuator on link one, it's called a pendubot. If there's an actuator on the second link, then it's called an acrobot. In this case, when we are trying to figure out the torques, we need to choose these gains such that the system is balanced in the upright positions. It's not very intuitive how you might go about choosing these gains. What we're going to do is we're going to use a technique called linear quadratic regulator to choose these gains. This video will focus on a pendubot in which link 1 is actuated. However, the code can be extended to control an acrobot in which the link 2 is actuated. Little bit theory behind linear quadratic regulator. We write the equations of the system as x dot equals ax plus pu. What we try to do here is minimize a cost which penalizes the deviation from x and the control. This minimization is done in Python using the control library. The minimization gives me a control u, which is minus k times x, where here x would be 4 states and u will be a single control variable. We'll be using the library control in Python. If you don't have this control library, you might want to install it by doing pip install control in terminal or command prompt on Windows. The variables q and r are matrices, which are user chosen, and one has to choose this to achieve a certain control. What we'll do here is we'll choose q to be n by n, or in this case 4 by 4 matrix of identity elements, and r would be rho times I, where I is m cross m. Here it will be 1. Rho is a tuning parameter which we can choose. If rho is much less than 1, it'll give very large gains and more aggressive control. If, however, rho is greater than 1, then we will not have too aggressive control, and the system will typically not be stabilizable under large disturbances. One issue, however, is that the system in question is not linear, which means it's x. The equations are written as x dot equals fx comma u. So we need to first linearize the system as x dot equals ax plus bu. In order to do this, we use what is known as Taylor series expansion. Let's consider an operating point, a reference set point. In this case, the vertical upright position. The state is 0, control is u0, and so we can write the equation as x dot 0 equals f of x0 u0. We then take a perturbation of x0 and u0, so we get this equation, and these terms here are the first order Taylor series expansion of the equation. We ignore the higher order terms. We can delete x dot 0 and f of x0 u0, and we end up with this equation where a is the gradient of f with respect to f, and b is the gradient of f with respect to u. Now we are trying to linearize the system in MuJoCo. In order to do that, we need to first understand the equations of the pendulum in MuJoCo. The equations are written in this form: m times acceleration plus frc by s equals tau. M is the mass matrix, q double dot is the acceleration, frc bias consists of gravity and Coriolis force, and tau is the external torque. For a pendulum, we would have the first element would be controllable, so that be actuated here. For acrobot, will be the second row which will be actuated in tau. So this is how we go about linearizing the system. We first write it as x dot equals fx comma u. We compute q double dot by taking the inverse of m, and we have this equation, equation 2. And so we can write a function f, which basically has certain inputs, in this case, the states. These first 4 are, and u is the control. And it outputs basically the rate of change of those state variables. What we'll do first is we'll write x dot equals fx comma u numerically, and then we'll go to the next step of linearizing the system. So let's do that. I have this code with me, which basically has a model of the double pendulum and then the Python file which runs it. So I'm going to run this file, and what you'll see, there's a pendulum which stays upright. However, if you let it remain for some time, it actually falls down. That's because there's no control. If you look at the pendulum.xml file, you see that I have, besides the model, I've defined two actuators on joint 0 and joint 1. I will be only using the actuator on joint 0 to simulate a pendubot. The first thing I said was we want to create a function which will give us the function f. So let's do that. Def, so create function x dot equals x u. So this should return x dot. So what x has is the the angles q0, q1, q dot, q dot 0 and q dot 1, and then u has the torque. Okay, so what we need to do is we essentially need to take the state and propagate to the model through using MJ forward. And once we do that, we can then compute Q double dot. So we'll do first. So we'll initialize Q pose 0 to be the first state variable. Q pose 1 to be the second state in X. And then on similar lines, we need to set the velocity. State 2. State 3. Now that we've done that, let's get the control. CTRL 0, that's the actuator torque on the first link, equals u 0. Now that we've set the state, let's propagate it through MuJoCo. We do that using MJ forward. Model data. Now this state has been propagated, and now we are ready to get the mass matrix and so on. So what we need is here is m dot equals inverse of m times the control minus FRC. Okay, so let's get all these quantities. First, we'll initialize the mass matrix to zeros. Next, we'll get the mass matrix by calling this function called mj full m. We need to pass the model. We pass our structure m, and then the mass matrix is saved in this variable called data.qm. Now let's take the inverse of m. It is using the numpy package linalg dot inverse m. Let's get the FRC bias. This will be an array dot q FRC bias 0 and dot q FRC bias. Now we've got FRC bias. Let's get the torque. Let's call that tau. And so that will also be an array. So now we'll have two elements to it. The first element is given by u0. The second element is 0. This is because the first link is actuated and the second is not actuated. Now we're ready to compute q double dot. It is going to be np.mat mul. We're multiplying inverse m with the difference in tau and FRC bias. So that will do np dot subtract tau FRC bias. Okay, so this part is done by the subtract, and then the inverse m is multiplied is using matmul. Okay, now that we've done that, all we need to do is create x dot, which is going to be np dot array data dot qvel, which is the rate of change of these variables. Data dot qvel1, and then the acceleration. So u double dot 0, u double dot 1. Okay, once we do that, we just have to return x double dot, sorry, x dot. So it's returned. And now let's just try to see if this actually works. So I'm going to call this an init controller. I'm going to initialize x0 to be zeros. And then u0 is also 0. And so to call it, we have x dot 0 equals f x0 u0. And then we want to print x dot 0. Seems like there's an error. This seems to be a typing error. Let's fix that right here. Then I need to end this bracket. Okay, now it should run fine. So it's vertical, and then we see that it prints x double dot. Everything is 0 here because we are at the upright position. Now that we've computed x dot, let's see how to linearize. We are interested in computing a and b. A is given by df dx, b is given by df du. And we've already computed f, which is our output, and then x is the one of the inputs. So to compute a and b, we see that df dx is given by this form, and b is given by this form. Okay, so in order to do this numerically, what we need to do is we need to create a function which has these 5 inputs, which we have done. We're going to compute the nominal f0, which basically propagate the 0 or reference position, in which case this is 0, 0, 0, which we've already done. Now, what we do is we perturb each element one at a time. This epsilon is a small number, 1 e negative 2, 1 e negative through 3. We propagate through f. Then we compute the first column of A by doing this subtraction, where this was this perturbation and this was the reference position, and we divide it by epsilon. We can do the same process for A to get the second column, third column, and fourth column. The same thing can be done B. B only has one column. So let's see how to do this. So we'll call a new function called linearize, whose goal will be to return A and B. And then we'll have, we'll get the linearization. So I'll say A, B equal linearize. Okay, let's initialize A and B. Now we know that A is, let's just define these sizes first. N equals 4 is the state space, M equals 1 is the actuators. So let's define A to be np dot zeros, n comma n. B is np dot zeros, n comma m. And then let's comment this for a second and just make this print A and print B. Just checking if this code works. So run this. See that it actually prints us A and B, which is nothing here but zeros. Now that we have, let's try to work on that methodology to compute A and B using linearization. So what I need is, I would need this code. Let's put it here. This code gives me x dot 0, which I need. Now I need to perturb each element one time. So let me choose a perturbation, 1e, say negative 2. And then I actually went ahead of time and then just computed all this A and B matrices. So this code here will compute the A matrix. What it does is the following. It basically assembles X with zeros. U is the nominal U0, which is here. Then it perturbs each element of X, as you can see here. Then computes each column by using this value X dot subtracted from x dot 0 and divided by perturbation. Okay. I also did this for b. So here x remains the same, 0, 0, 0, 0, but I need to perturb u. And so I create u, I perturb u, I do the same call, but this time u is perturbed, and then I can compute the column of p by doing x dot minus x dot 0, which was computed right here. Now that we've done this, we can run this code and see what a and b comes out to be. We see that a and b are now not zeros, but these values. Okay, now that we've got a and b, now our goal is to create the linear quadratic regulator. So let's see how to do this. In order to compute the gain matrix K using LQR, what we do is we import the control library and use control.lqr, whose inputs are A, B, Q, and R. We've already computed A and B. Q and R are user chosen matrices. And then to test the controller, we'll add some disturbance, which we'll see next. Okay, so as I said, we need to first import the control library. So import control. Now we can get the gain by doing control.lqr a, b, q, r, where we have to still define a, b, q, and r. So let's use q to be the identity matrix of size n. So let's define n here. N equals 4, n equals 1, r equals b dot I m. Okay, and then we want to multiply this with 1e negative 2 to weigh the R matrix. So this will give us R. Let's k, sorry, in print k equals k, and let's run this. And we see that it actually prints k. Now that we've got k, now let's see how to use this. We need to set the controller here. So what I'll do is apply control u equals minus k times x. So we need to initialize the state. State is going to be np dot. So we need data dot q pose 0, data dot q pose 1, data dot q val 0, data dot q val 1. This is our state. And then we need to multiply minus k times dot x. Now k is not available here, so I need to define it as a global variable. So I can access it. I similarly need to define it here as global k. So once it's created here, it can be called inside here. Okay, and then final step is to set ctrl0 to be u. Okay, let's see how this runs. Okay, looks like I was just missing SE, and then if I run this now, it works. Now the pendulum is upright and it's not moving, and that's because the controller is doing its job. Now, in order to really test this, I need to perturb the system. So what I'll do is I'll apply some perturbation or disturbance talk in this case. So apply disturbance talk. So what I'm going to do is I'm going to create disturbance talks with the mean and standard deviation, and then apply that. So let's create that. Tau disturb mean. So the mean value, let's say 0. Tau disturb deviation, let's put some value 20. And so now we can create the disturbance talk on link 0. So np.random.normal disturb mean disturb here. So what this does is essentially creates a normal, use a normal distribution with a mean given by this and deviation given by 20, and then creates this disturbance. We can do the same thing for link one. So let's put that, for now, let's just put it 0. And we need to propagate that through the system. For that, what we need to do is we say data.qfrc slide 0 equals tau e0 and data.q slide 1 equals tau. So I'm only putting a disturbance to link 1, the first link which is controlled. Okay, so here is the pendulum with a slight disturbance on link 1. You can see that it's struggling, but it's still able to keep this upright. Okay, now to make it harder, what we can do is we can actually add a disturbance to the second link. Remember, the second link is not controlled. We'll actually add it slightly less than this one, so 1/4 of 20. And you can see now it's struggling, but it still is able to keep the pendulum upright. So this is how you can linearize the system and use LQR to create a controller and test it by adding a disturbance.